Our lecture tonight is joint with the university's Advanced Space Concepts Laboratory and is on a topic that I'm pretty sure James Weir would be leaning forward in his seat to hear about. Alan Bond's company, Reaction Engines Limited, are designers and developers of advanced space transportation and propulsion, according to their website. Alan was born at Ripley in Derbyshire, as was Barnes Wallis. He worked at Rolls-Royce on the British Blue Streak rocket project and then at BAC on other rocket work. From 1976 to 1990, he was with the UK Atomic Energy Authority, working on various nuclear fusion and advanced space propulsion systems. He originated the HOTOL spaceplane engine design in 1982. I'm sure he'll be touching on that later in his lecture. Alan formed Reaction Engines Limited in 1989, joining it full-time in 1990, and is its current managing director. So Alan has a uniquely broad and long-term perspective on advanced concepts for space and near-space transport. I'm delighted to welcome Alan Bond to the University of Strathclyde and call on him to give the first James Weir lecture.
Thank you very much for that glowing introduction, Jason. And I have to say, I hadn't realised that this was going to be the honour of the inaugural James Weir lecture, so I've got an awful lot to live up to here. The talk that I gave up until a couple of years ago was very speculative about what we could do, what advanced propulsion techniques offered for a distant future, which was sort of vaguely linked to some plan in my mind and people at the British Interplanetary Society and so on. However, I'm pleased to say that over the past 2 years particularly, but numerous events, perhaps spanning back 4 years, have led to a situation which at this very moment, everything that I'm going to tell you tonight is actually happening. It's not something which is a vague concept which may or may not come about. It may still not happen. We in Britain are extremely good at snatching the iron from the fire at the last minute. But as things stand tonight, the British government has put an awful lot of effort into bringing space to the fore, and that effort includes the work at Reaction Engines. And for the first time in many years, the British government is actually considering that we will look at the enabling technologies of getting payloads into space and not just being a nation that exploits other people's capabilities of getting things into space just so that we can do the space science or the communications and so on. We're actually interested in providing the actual technology to do the job. Now, my own background was very much Blue Streak back in the 1960s and early 70s. Black Arrow. Black Arrow is a classic example of British ingenuity. It was pretty much standard rocket technology, but nonetheless extremely well engineered, which is what we've tended to do in the UK over the years. And so this vehicle had an extremely good mass ratio, rather a funny looking shape, very heavily optimized to get the best out of a vehicle of this size. Black Arrow wasn't much heavier than V2 at takeoff, and yet one of the satellites the only satellite that it managed to launch is still up there, and a reminder to everybody that we in Britain, having shown that we can do something, sort of get bored rather quickly and move away from it. Blue Streak, we developed a respectable weapons system. There are people who are advocates that we were sort of robbed when we lost Blue Streak. I'm not one of those advocates. If you go to East Fortune, just down the road here, go on a day when they'll let you into the little hangar at the back where they've got, I think it's the F-16 round of Blue Streak, and alongside Blue Streak is a Polaris A3 missile, and you will see there is no comparison as a weapons system. And so what we did, we offered this to the Europeans, we built a multi-stage rocket out of it, and then of course we pulled out the first stage, which left the Europeans sort of a little bit lost for what to do next. Just a few, 100 miles down the road at British Aircraft Corporation, in the 1960s, people there were already looking at trying to get reusability into launches. And a very successful study this was, but sadly, again, it never saw the light of day. And then in the mid-1980s, we started on the HOTOL project, and that came from the fact that in the early 1980s, I'd managed to adapt some thermodynamic principles from nuclear engines that I'd been working on and found that they could be applied to air-breathing engines, and I'll talk about that in more detail later in my talk. Excuse me. But the main thing is this study got underway. It had its problems, and I'll mention what those were. But the biggest problem of all was this guy, and if the Conservatives win the election, I'm afraid he, like Dracula, may be back to haunt us. So launches then today, things have moved on a bit from those days of Black Arrow and Blue Streak. In Europe, after we pulled out our first stage, the Europeans went on and developed rather outstanding technology ultimately. Ariane 4, which came before it, was a bit basic, but Ariane 5 is a very sophisticated modern launch vehicle. The good old faithful Soyuz launcher, of course, is still with us, derived from a ballistic missile. Now must be by far the longest serving launcher that we have. And of course the Space Shuttle, which was an attempt to build and derive a reusable vehicle. Prior to this vehicle coming into existence, the Space Shuttle was going to be a two-stage flyback, piggyback aeroplane configuration, and that went to Congress, and Congress threw it out and said come back at half the development cost. Well, they did come back at half the development cost. The orbiter survived, which is really a reusable space station that you send into orbit. It happens to have some rocket engines strapped on it. But this big drop tank gets thrown away, and the solid boosters are recovered, but that's really a political recovery more than an economic recovery. The economics of operating those boosters, towing them back from the ocean, stripping them completely bare and rebuilding them, really is a questionable economic activity. So, big problem with all of this, it's extremely expensive. You've got to develop the vehicles, which cost you many billions of dollars to do. You then have to produce them on a regular basis, and of course you never see all the components again, with the exception in this case of the Space Shuttle, and that is now nearing the end of its life. The question that has vexed me right from my first brush with rockets is, do we really need to throw these rockets away? And do we really need to go multi-stage? Could we have something which is single stage, like an aeroplane, which can go into space, do its job, come back, and then a few days later do it again? I think air travel would have been pretty slow off the ground if every time we did a flight to America, you threw the aeroplane into the ocean at the end of the mission. So, one of the problems we've got, a dear colleague of mine, Bob Parkinson, points out that the Earth is 10% too big. Had we been able to live on Venus, then getting into orbit would be much easier, and rocket engines that we know and love would enable us to do it. So it's a little bit of a cosmic joke that the Earth's just a little bit too big. However, consider if we'd lived on a planet twice the size. If there are people out in the universe and living on planets twice the size of the Earth, maybe they're not here because they can't get off the damn place that they were born in. So, with near-term materials and technology and discounting the use of ozone and fluorine, it becomes obvious that we've got to make use of the atmosphere. There is, without going nuclear, and that's the subject of a different lecture, we must use the atmosphere both as a reaction mass and also for its chemical energy. I'm told that I can sort of get a little bit more technical with the people in this audience than I'm usually used to, so I assume that everyone here is familiar with the sort of rocket equation normally attributed to Tsiolkovsky, but was actually being set as standard exams at Cambridge for university graduates during the mid-19th century. But the object here is, if we want to get into orbit, we've got to build a system that we can put about 9.5 kilometers per second delta V into the vehicle. And so here we are. If we're going to do that, then the vehicle has to have, give or take, a mass ratio of about 8. That is, at liftoff, it weighs 8 times as much as it weighs when it's burnt all of its propellant getting to orbit. And that's quite a tall order. Now, one option is to go air breathing all the way. You build a scramjet or something like that, and you put a lot of effort into the air breathing side of it. But we can consider this a little bit more logically. Suppose that we take the rocket, which can very nearly do this job, and what we do is give it a bit of help. We just put sufficient air-breathing propulsion on it to reduce the job that the rocket engines have to do. And along here is the Mach number at transition from air-breathing to rocket. And just have a look at what it does to the mass ratio. So suppose that we could fly it up to Mach 1 before we turn the rocket engines on. Then we get the mass ratio down to about 7.5. If we get to Mach 3 before we turn the engines on, it's about 6.5. If we went up to Mach 7, then we can get away with a mass ratio of about 5. Now, of course, we're putting all of the air-breathing kit and wings and all of those things on there, so they have got to pay for having that on board. And the Americans have put quite a lot of effort into looking at going up to Mach 10 to try to get the effort that you've got to put into the rocket really down. But again, if we return to a little bit of logic for a moment, what we see is that air breathing is difficult. This is a sort of fairly standard perfect gas relation relating the stagnation temperature to Mach number. I've simply put 220 K in as a sort of typical temperature at altitude. And you can see the stagnation temperature is climbing astronomically as you start to put more and more in with the air breathing. And really, by the time you're above Mach 5, if we just pop back to Tsiolkovsky, we can see that we're getting most of the benefit. But we're managing to avoid most of the stagnation temperature implications. And so if we could find an engine that would get us up to Mach 5 air breathing without introducing too much of a weight penalty, then we should be starting to win out. At the National Gas Turbine Establishment, now long subsumed into other establishments, I'm afraid, Jefferson Beaton in 1962 came up with the concept of the liquid air cycle engine, in which air passes into an intake and a heat exchanger. The liquid hydrogen fuel is simply pumped through this in sufficient quantities to liquefy the air, and then in this rather simple little diagram, pumping the liquid air into a rocket combustion chamber for the early part of the air-breathing ascent. And the advantage of that, of course, is that when you finish with the air-breathing bit at some unspecified Mach number, you can then go on to replace the liquid air with liquid oxygen that you're carrying on the vehicle. So this concept goes back a very long way. There are huge problems in simply what's put there, but here you can see that the liquefaction is a simple-minded process of simply putting cold liquid in, cold air comes out, and hot gaseous hydrogen is the product. Well, it turns out that if you sort of get to grips with the thermodynamics and invoke entropy as well as conservation of energy, then there are some interesting tricks that you can play. And for those of you who are familiar with entropy, you'll know that there's a perfect gas relationship for the change of entropy of a fluid, which relates not only the temperature ratio, but the pressure ratio that the fluid goes through. And therefore, if you set the delta entropy to 0, you can trade a temperature ratio for a pressure ratio. And so if instead of using the hydrogen simply as a coolant, you use it as the heat rejection system for a thermodynamic cycle, lots of things are possible. And so having given you that this tempter, I shall come back to that in a little while. As Jason referred to, the immediate product of the work that I did on this in the 1980s was the HOTOR vehicle. And you can see that we had what was essentially a rocket, and we put some wings on it. And you can see that being rocket engineers, we put all the engines on the back of the vehicle, and we had the liquid hydrogen tank in this long forebody. That was a fundamental mistake. Nonetheless, it was an inspired study, and this still remains the only study in the open literature where you can actually go and find everything that was done. British Aerospace and Rolls-Royce really gave this a very, very thorough going over. And at the end of it, the conclusion was that we'd got some serious problems, but nonetheless the concept was fundamentally sound. And the serious problem was, that by putting the engines on the rear of the fuselage, we had determined absolutely where the centre of gravity was going to be. And the problem with this configuration is that as you accelerate up the Mach number range, the lift on the forebody remains more or less constant, but of course the lift on the wings falls off as 1 over the root of m squared minus 1. So you have a tremendous move forward of the effective centre of pressure of the configuration. And at Mach 5 we were trying to battle with a 2,000 ton-metre moment, trying to pitch the nose of the vehicle up. And that result required huge flaperons. It required an equally huge power supply to drive it. And this vehicle became a transport system for hydraulics into low Earth orbit. So after a lot of thinking, reaction engines sort of came into being at the end of the 1980s, and we tried to understand what had gone wrong, and the answer was don't put the engines on the back of the fuselage. And because it turned into a rather long pointy sort of shape, I'm sorry to say that I remember the Skylon sculpture at the Festival of Britain in 1951, and so we named it Skylon after this very inspirational British exhibition. Unfortunately, Jason told me tonight that he gained his inspiration from a project I worked on when he was 11, so we won't dwell on that further in this talk. What do we want out of a space plane if it's going to have commercial characteristics? We want it to be reusable. Single stage, we don't want to be sort of getting an airfix kit at the launch site every time we do a mission and have to put it all together. We'd like it to be unpiloted. A lot of people sort of don't really like that, but a pilot hurts you in several ways. First of all, you have to keep him alive, so we've got to put a life support system on, which is a waste of payload. It means that in the development program that you are constrained again by having to keep the pilot alive. So most of the systems that you put onto the program have got to be developed like a civil airliner, or at least a military aircraft, rather than a missile program. And finally, of course, the pilot needs training, and the whole thing results in a huge complex of simulations and so on. And throwing the pilot off halves the cost of the project. Now, I often find that there are people who dispute that, but they come from time after World War II, when during the sort of 5 years after World War II, we managed to kill 37 test pilots. Well, people take a dim view of that these days. And so nowadays, unpiloted is deemed best. One of the advantages of aircraft is you can abort the mission. A lot of aircraft take off and have to go back because something has gone wrong. It's got the capability, both in terms of redundancy, but also in terms of its design, to actually not carry out the mission but not lose the payload. We need user-friendly operations. You've all seen what goes on at the Cape and various things like that, where a huge kit of parts comes together. You've got to assemble it, put it together, get it out to the site, check it out, and soon, in about 2% of cases, we get that wrong and it goes into the nearest ocean instead of into low Earth orbit. Now, a very important point is re-entry cross-range. Douglas Aircraft Company in the 1960s actually convincingly showed we could do single stage to orbit with a rocket-like vehicle, with a very large Apollo capsule-like base which you discharge the engine exhaust into, and you'd re-enter it base first. That concept I worked on for many years. I'm quite convinced it would work. However, the cross range is limited to about 200 kilometres. That means that either side of the ground track you can only pull about 200 kilometres in either direction. And this means in a commercial operation, you've got a guy on the ground waiting to fly a customer's payload, and your vehicle's still in orbit, waiting to cross the landing site for you to get it back. And so it's quite important to have a high lift ratio during re-entry. of the order of 3, whereas other concepts of the order of a half for the sort of ballistic rocket. And this will give you a cross range of over 3,000 kilometres, which means that you only need to come to the pass before or after the one that would cross the landing site, and you can still pull sufficient cross range to land the vehicle. And of course, these days we all like to make claims about environmental impact, and I won't dwell on that. The configuration that we came up with then is engines on the wingtips. That gets rid of the CG problem. Of course, you can move the wing wherever you want, and the CG goes with it. You put the payload over the CG so that when you've got a payload on board, it minimises the movement of the centre of gravity. During, you've got liquid hydrogen and you've got liquid oxygen. And during the air breathing ascent, you burn the hydrogen from the rear tank, because this still suffers from the same problem that HOTOR had, but now it's much smaller. There's only about a 200 ton-metre moment. But by burning the hydrogen out of the rear tank, the centre of gravity tracks forward as well. And therefore, you can nicely cancel out. There is a residual problem, but you can trim that out with the Canard foreplanes. I don't want to dwell too long on this because I want to talk about the engines predominantly. With a liquid hydrogen vehicle, the good old faithful stress skin structures that have stood us in good stead since the 1920s on aircraft design are no longer applicable. A lot of people have looked at hydrogen-fueled aircraft and come to the conclusion that they don't really work, and that's because they're stuck with the idea of the stress skin structure, brilliant innovation though it was. But there was an earlier technology, which was airships. And liquid hydrogen really is the same problem that you have with airships. It's a very low aerial loading of the vehicle. And it turns out that you really need to build yourself a Warren Girder structure for the aircraft, put an aeroshell over the outside of it, made out of a fibre-reinforced glass material, which if we have a look at a temperature-specific strength chart, we've got silicon carbide reinforced titanium, and we've got at the high temperature end carbon-carbon and silicon carbide. And there is this material, which is a fibre-reinforced glass. The original material was silicon carbide fibres in Pyrex, immediately a success. Of course, the Pyrex sticks to the silicon carbide and gives a very good material. There are now other glass ceramic matrix materials, and in this region here is a very nice material which we developed in this country, which has got good temperature characteristics and good specific strength characteristics. We're currently working with a French firm called Pyromeral, and we are actually testing some of their material for monatomic chemistry compatibility in a glow discharge system that we built at Reaction Engines. And so a airship-like structure with a glass ceramic aeroshell. One of the advantages of having the hydrogen tanks on board is that Skylon re-enters about 10 kilometres higher than the space shuttle. And as a result, it doesn't reach such high temperatures. It has a larger heat soak, and that's one of the problems of things with low ballistic coefficients taking a long time to re-enter. But by carrying 200 kilograms of liquid hydrogen for the return journey and vaporizing it in all that tankage, which you can see is underneath the aeroshell, then we can cope with the heat load problem. There seems to be absolutely no other application for this material. If there is a God, he intended these materials for the aeroshells of re-entering space planes and no other application whatever. Skylon is quite a mature project. Kinetic some years ago did tests at Mach 9 and Mach 12 in the gun tunnel and in the flow visualization tunnel at Farnborough, and you can sort of see the sort of flow structure. The gun tunnel tests did show up some shock interaction heatings and shock boundary layer interaction heating problems. We anticipated the shock ones, but we'd missed the shock boundary layer problem. But again, I don't want to dwell on that. So Skylon, configuration C1, which is the one that I've mainly been talking about, 12 tons to low Earth orbit, 10 tons to the International Space Station, a 200 cubic meter payload bay, 4.6 meter diameter payload. and about 275 tons at the start of roll at takeoff. So a quite reasonable sort of machine. It is 82 metres long, and so the fuselage is about the size of a 777 fuselage, and that's because of the liquid hydrogen. Even though we've only got about 70 tons of liquid hydrogen on board, with something which has got only 7% of the density of water, it's obviously a real disadvantage. We are currently revising this to the D1 standard with a 15-ton payload, because this design is now rather ancient. So a picture's worth 1,000 words and a video's worth 1,000 pictures. So just a very quick run through this. Gives you some idea of the sort of structural elements of the vehicle. Payload bay, liquid oxygen tanks, the hydrogen tanks, the glass ceramic aeroshell, and the engines in the cells on the wingtips. And an undercarriage. HOTOR, could never take off on its own undercarriage, but Skylon is able to do that. And in order to accept the energy of a rejected takeoff, we are proposing to use water-cooled brakes. And on a successful takeoff, you throw away the 1.5 tons of water that it takes to cool the brakes if you need to reject it. Otherwise, Skylon would be a transportation system for brakes into low Earth orbit. The idea is to try to make the loading of the payload extremely simple. I don't know what the current cost is, but 15 years or so ago, it used to cost $5 million just to put the payload into the shuttle payload bay. We're trying to look at the concepts of containerized payloads so that your spacecraft arrives factory fresh to go with the Skylon into orbit. In terms of fueling it, the tractor tows the vehicle out onto the start of the apron, and then liquid hydrogen, liquid oxygen, liquid helium, which is needed for pressurization, and as you will see in a moment, engine operation transferred into the vehicle. And then the tractor pulls the vehicle to the start of the runway. One of the serious problems with the design of undercarriages is all the taxiing that aircraft do around airports. It twists the undercarriage out of the supports in the wing, and so we do the minimum amount of movement on the undercarriage possible. The engine, as we'll come to, is air breathing right from square one. Unlike a ramjet or a scramjet, this engine is operational right from a standing start, and under air breathing conditions will drive the vehicle into to an altitude of about 26 kilometers and Mach 5. Obviously, you've got to close the intakes when you do the transition to rocket, because eventually you're going to re-enter into the atmosphere, and you don't want the high enthalpy flow into the intakes during re-entry. These engines also have a bypass system, which I'll just briefly mention later. We have to close the bypass system off as well. On orbit, there's a orbital maneuvering system. You can see the OMS engines sort of putting in the final velocity there, and 38 reaction control thrusters for attitude control and so on orbit. And there's an auxiliary propellant supply in the vehicle mounted in the tail that provides a sort of gas main around the vehicle to provide gaseous hydrogen, gaseous oxygen for fuel cells, auxiliary power supplies, and also the thrusters. The vehicle can carry a range of payloads, including a manned passenger module, which is depicted in this slide. And as I'll mention at the end of the talk, we think that this is the first part of an entire space infrastructure. And if you're going to build equipment in orbit, you need an on-orbit assembly facility, which is what's depicted here. During re-entry, the vehicle enters the atmosphere at a very high angle of attack, initially about 70 degrees, in order to lose as much velocity as possible in the first instance. But then during the re-entry, it undergoes a gradual pitch down to about 11 degrees, which gives us its maximum lift-to-drag ratio at round about Mach 11. At round about Mach 9, we get authority from the tail fin. Prior to that, we have to use, same as the Space Shuttle does, the lateral yaw thrusters in order to control yaw. But we can't control the pitch during re-entry on the foreplanes. We have to carry water as a coolant for the foreplanes for that part of it. And then finally, the vehicle comes in for a dead stick landing, just like the shuttle. Okay, so that's the vehicle essentially, and now I want to come on to the engines. The engines are at first sight quite complicated, and so I've produced various diagrams at different phases of trying to present this, and I'll try this one on you and see whether you like this. I mentioned that what we actually want to do to try to reduce the amount of hydrogen required to cool the air is be a bit cleverer than just pump it through the airflow to cool it. So we'd like to use the hydrogen as a heat sink for a thermodynamic cycle. So here's the hot air, the heat exchanger, which transfers heat through the cycle, which we can then drive the turbine with. So rather cunningly, some of the heat never actually leaves the air. It actually gets immediately put back into it through the compression process. And therefore, we don't have to remove all of the heat from the air with the hydrogen. The only part that gets removed is by the heat sink function, which eventually finishes back in the combustion chamber anyway. So this is the first sort of chapter, or second chapter normally, of your thermodynamic textbook on heat engines. And that what we're doing is actually getting some work out of the heat transfer process. It gets a bit more complicated when you try to start putting some of the equipment in, so this is sort of a semi-real schematic. Here's the pre-cooler, and what we've done is introduce a helium loop actually into the engine. On HOTL, we did all this with a hydrogen loop, but everybody was very worried about what happens if a pigeon goes in and breaks the pre-cooler and all the hydrogen then goes through the engine. That's something that could be debated, but anyway, we chose to use helium. The main reason being that the Inconel materials that we'd like to use in the pre-cooler don't like hydrogen. With helium, you can use some of the better nickel alloys, and we in fact use Inconel 718. So a helium circulator takes cold helium, cools this, and then passes it through another heat exchanger, which is heated by a pre-burner, so that helium is always at 1180 Kelvin at this point here. That then goes to drive the turbine, which is driving the compressor, before rejecting heat to the liquid hydrogen flow, and the whole of the hydrogen flow goes to the pre-burner. The airflow bifurcates. Part of it goes to the pre-burner, a variable amount to the pre-burner depending on what Mach number you're at, and the rest of it meets up with the rest of the hydrogen in the combustion chamber. Now the advantage of this is that you can vary the temperature of the pre-burner so that this temperature here in the helium loop is always constant at 1180 K. So with the exception of this bit of the engine, the rest of this engine doesn't know what Mach number it's flying at. It's a drag racer engine, it's not a Formula One cruise engine. And what we need if we're going to have a successful air-breathing accelerator is an engine which is Mach number insensitive. And until we reach the temperature limits in the pre-cooler, that's exactly what this engine is. Once you start to put it together in reality, it starts to get a bit more complicated. You can see that the pre-cooler is quite a dominant part of the engine, the turbocompressor, the rocket engines, and then all the thermodynamic gadgetry is in here. It's an annoyance that the captured airflow in a supersonic intake does not match the airflow of the engine, and the captured flow goes roughly as 1 over the Mach number. So at low Mach numbers, very much more air is entering the intake than you need. So you bypass that air around the engine. Even with these clever thermodynamic tricks, the engine still takes far more hydrogen than you need for combustion in the main chambers. So that extra hydrogen is added to the burners in the bypass duct. And at this point, there's usually somebody who says, so what this really is a turbo ramjet. But it's not, because in a turbo ramjet, you use the gas turbine to accelerate you up to some Mach number. You then turn the ramjets on, and it's the ramjets that continue to the higher Mach numbers. And this is exactly the opposite. At Mach 5, there is virtually no flow down this at all, and all of the thrust is developed by the main engines. The maximum thrust from the bypass duct in this case comes at round about Mach 3 to 3.5, where it gives a very useful contribution. So some parameters then. The nozzle area ratio is of the order of 100, a bit more than that in current designs. In the air breathing mode, the combustion pressure is about 102 bar. If you think about a gas turbine, then that is sort of round about 30 bar. So that's a very sporty compressor, but nonetheless, 140 bar delivery compressor is quite doable. The rocket combustion pressure is sort of state-of-the-art, 145 bar. What other things are of equivalence ratio? During air breathing, the equivalence ratio of the engine, that is the number of times the hydrogen that we need above stoichiometric, is about 2.8, whereas the old LACE engine was around about 4. So we've made a substantial improvement in that. And as a consequence, we get a theoretical effective exhaust velocity of about 16 kilometers per second, compared with a theoretical of about 46 kilometers per second. And we are currently looking at new designs of Sabre engines, Sabre 4 as it's known, which approaches that sort of number. But I shan't be saying anything about that tonight. Pre-cooler construction then. We've shown that with a pre-cooler we can actually do this job and do it rather well. But how do we make it? Well, the designs that we currently work on involve huge numbers of extremely small tubes. The tubes that we're dealing with are less than 1 millimeter in diameter, made out of Inconel 718. And they are modular in that we have a header, a sort of Swiss roll of tube sheet to an inside header. The air flows radially in through the heat exchanger, and the cold helium flows in through the header, out along this spiral track to the outside, and then out here. So this heat exchanger has got the air in crossflow, but the overall effect of the heat exchanger is pure counterflow almost. And these heat exchangers have got extremely high effectiveness, 92, 95% effectiveness. And here's some that we did earlier. This was one of our first ones. What I want to emphasize here, you're looking at a tube here. It's 0.88 millimeter bore with a 30 micron wall. And our current tubes are of that sort of order. This is an earlier research heat exchanger that we built, and a lot of our effort goes into, after all of this clever stuff, into the nitty-gritty of how do you braze these tubes into the headers. And that is quite a major task. When the air enters the engine, it's about 1,000 degrees centigrade. By the time it's been through the pre-cool, it's about minus 140. And of course, there's a lot of water vapor, even in the air in this room at the moment. And if you just try to do that trick, what happens within about 3 to 5 seconds, the whole thing is frozen absolutely solid. So a lot of our activity in this research tunnel was to find a way of preventing frost formation. And what you can see here is this is the pressure drop through the matrix over a period of about 11 minutes, I think, in that particular test. And you can see that we solved that problem. But the bad news is I'm not going to tell you how we did it. So you can see here the temperature on the air side is down at sort of minus 80. And during the course of the test, the coolant side temperature follows a programmed so that we can get as much information as possible, starting at sort of minus 50 down to about minus 150. So we did solve the frost formation problem. And there's an example of a module. And These are modules that were built under a European Space Agency contract. This is for a different engine, a different project I'm not going to dwell on tonight, which is for a civil airliner application, a Mach 5 airliner to do Brussels to Sydney in 4 hours and 40 minutes. And so if anybody wants to know more about that, then I'm happy to answer questions later. But the important thing for the moment is the pre-cooler technology, and you can see that we're doing pretty good at brazed joints these days. And we're very, very close now to getting 100% brazed joint success. If we don't get 100%, we simply plug the few percent of tubes that leak. Now, heat transfer in these engines is extremely important. Excuse me. And it turns out that the whole thing is dominated by the heat transfer coefficient on the air side of the pre-cooler. If we could improve that, then quite major miracles are possible with this type of engine. We currently have a student from University of Bristol doing her PhD working on heat transfer enhancement on the tubes in a matrix like this. This is a flow visualization. We operate these heat exchangers pretty much in the laminar regime, laminar to transitional. And so what she is looking at is whether we can modify the surface of the tube without putting up the weight too much or the pressure drop. Now, to give you an idea of the problem, the wall thickness of the tubes when we finish with them is about 15 microns. They're much thicker than that when we get them from the manufacturer. But we then process them down to about 15 microns for a real engine. We've moved on now. We've solved virtually all of the problems, and one of the things that I want to say is that we are no longer into research on these engines. We are into development, but there are no issues left in this project where we need to, for example, go and talk to DARPA, which is a sort of frequent suggestion. We don't have any research issues left, but what we are in the process of doing is using a Viper jet engine with a pre-cooler mounted in front of it, using liquid nitrogen as the heat rejection system and a 200 bar helium loop in order to demonstrate that we can actually build these pre-coolers and operate them. We've had this facility ready at Culham now for quite a few years, and thanks to ESA grants and private finance totaling about £6 million, we're now in the process of getting to the point where we're going to be testing this in anger during the middle of next year. We're currently building these pre-cooler modules. We've set up our own production plant in Abingdon, and we've also acquired 2 other manufacturing companies which are part of Reaction Engines to build all of this equipment. So Reaction Engines has moved on from 3 people in their lounge with some faxes now to quite a sizable company with a lot of facilities to do this. We would also like to try to get some clever nozzles, because I mentioned that the area ratio was 100 to 1, and under those circumstances the nozzle is very heavily separated. For a long time there has been in the literature the expansion deflection nozzle. Now, I don't know if you can see just inside here there's a sort of pintle, which means that the flow in this nozzle comes out as an annular sheet filling the nozzle completely, and you can just see the film there in this engine which we built and tested a couple of years ago now. It's very short, of course it's adiabatically cooled, but let's see if I can go back and do that again in case. And in particular you'll see that all the action is in this sort of few millimetre thick layer here at the edge. We injected salt water into that to make it visible. Normally you can't actually see that in operation. The other aspect of these engines are the turbines, and this is an experimental turbine, which is a counter-rotating turbine with no stators in it. Now, I glibly showed you a cold air compressor driven by a helium turbine. Now, helium, low molecular weight, high temperature, the turbine wants to run fast. The air is cold, miserable molecular weight, and therefore wants to run slow. And the way to do this is to split the compressor into two spools, to throw the stators out of the turbine and have the turbine stages contra-rotating, each stage rotating relative to the opposite direction of the one after it. This way you can fool the turbine into thinking it's running twice as fast as it really is. And as a consequence of that, the turbine efficiencies can be very good. 94% we achieved in this experimental turbine. The blading for this was designed by the von Karman Institute in Belgium. And there you can see rotors 1 and 2 and rotors 2 and 4 with the inlet plenum. There are other heat exchangers, and we've got ongoing research on that. To give you an idea, this is a CAD drawing, but we're looking at channels which literally you can't see. It's a bit like looking at a CD when you look at one of these things. We're looking at these channels are sort of 50 microns with about 6 micron wall actually separating them. And those are a vexing manufacturing problem which I won't dwell on any longer. But we've also investigated silicon carbide manufacturing at TEMMAT, and in this case this is reaction bonded silicon carbide, which they flood with, basically start with graphite, flood with liquid silicon, which converts it to silicon carbide. And one of the problems we get is these little silicon spherules which fill the channels, and we have to get those out. But it looks as though this technology can be developed quite successfully. They really did quite a rather simple bit of development work for us, and it looks as though that is with us. At the present time, we're looking at heat exchangers which are with very good entropy conserving characteristics, delivering about 300 megawatts per ton of heat exchanger. And that is more than adequate to get successful engines. And we are nowhere near the physical limits at that, but what we are pushing at the moment is the manufacturing limits. The whole future of this is manufacturing the components. Skylon then, just to sort of reiterate, it's about a 9.5-year program. It's going to cost about £7 billion. Each vehicle off is going to cost about 190 million if we produce 30 vehicles. And we think we can build a vehicle that will survive about 200 flights before it goes to the crusher. That means an engine lifetime in each vehicle of about 50 hours. And that helps a lot. We're well out of creep issues and so on. The recurring cost for a flight, therefore, comes down to about £5 million pounds a flight, so let's say $8 million. Currently on the Space Shuttle, a flight is about $700 million. Now, what I haven't put in that figure is the insurance. The insurance is a vexed issue. Third-party insurance could quite easily come to $10 million a flight, and the first-party insurance would be of the order of $5 million. So 3/4 of the flight costs with a vehicle like this in the early stages of entry to service would be insurance costs. The thing that I want to point out is the launch price pays everything in this case. There's no subsidies, as there are with the Ariane vehicle and so on. Spaceports are commercial, and what we hope is that there will eventually be something like a dozen or so commercial operators competing with the payloads to go. And the objective is to move the whole of access to space into the commercial arena. So having said that, I just want to spend about 10 minutes just briefly going through what the consequences of that will be. It's not new. People have been looking for the last 60 or more years at having a space infrastructure. Now, I really wish that we could just dump all the bits in orbit like that and they'd stay there, as the early pioneers sort of envisaged. The reality is that each of these components is in its own orbit around the Earth, and therefore all this lot jostles around every time it orbits the Earth. So you have to have a facility to actually do it in. Some of the equipment that we need for Skylon is an upper stage, because one mode of operation is to not go quite to orbit, but boot the payload out with its own propulsion stage and let it go to orbit and land the aircraft downrange, and then by one means or other get the aeroplane back. It is possible on orbital missions to go into resonant orbits now. It's just a coincidence that at 300 kilometers, Skylon is resonant with the geostationary transfer orbit. So when Skylon does 7 orbits of the Earth, the upper stage does an orbit out to geostationary orbit altitude and back again, and it meets up with the Skylon with a little bit of orbital manoeuvring absolutely accurately, so the stage can be recaptured and returned. I've already mentioned that we can put in a passenger module that can carry 20-odd passengers to an international space station. My colleague Mark Hempsel has put a lot of study into that. And we think that we could fly research laboratories on specialized missions. We have looked at a stage which we call the Flute stage. I'm told that a flute is a Dutch barge of some description. I didn't think of the name, so don't blame me. And the Flute stage is essentially using the Vinci engine, which is being developed in Europe at the present time. Again, liquid hydrogen, liquid oxygen, so it's common with the Skylon vehicle, and with hydrogen to pressurize the stage. And there you can see the hydrogen tank in the Skylon payload bay. It arrives on orbit in the propulsion module and LOX tank, the hydrogen tank, and of course payload being conveniently labeled payload. And that, of course, assembles into a orbit transfer vehicle configuration. To go beyond Earth orbit, one of the things that we looked at, mainly to make sure we were getting Skylon right, was could we do a Mars mission? And the answer is you use Skylon to ferry into orbit modules of various bits and pieces for assembly on orbit, and then put together this whole stage essentially in this orbital base station, as we call it, which is an orbital assembly facility to keep captive all of those bits in the von Braun slide. Skylons would regularly ferry to that. A Skylon can be turned around in about 2 days. So a Skylon could ferry a payload to this base station, land, it could go through its checks, be refilled. 2 days later, it could be back up there with another payload. 522 payloads would get you 3 vehicles together, which could then give you a vehicle like this, which you could fly 3 of to do a Columbus-type mission to Mars. And here you can see a ferry vehicle using carbon monoxide and liquid oxygen as propellants. Conveniently, you can make those out of the Martian atmosphere using a nuclear electric plant. And therefore, we have looked at the possibility of expanding. We've looked at a mission flown in 2028 because it's a quiet sun in 2028. But I personally think this is probably going to be middle of the century rather than the first quarter of the century. Let me come to some conclusions then. We require a low-cost and reusable transportation system, not just the space plane, but all the elements. But it's quite clear that the reusable launch vehicle is the most difficult step. It's the so-called von Perke paradox, that the most difficult step of getting anywhere in the universe is getting off the Earth's surface. And although this 10% too big is a curse, we're fortunate that it's not 50% too big or bigger. Otherwise, we'd really have a problem. Skylon will, I'm quite convinced, transform how we use space and how we access it. The spacefaring nations of the world at the moment, Japan, India, America, etc., the Europeans, are continuing to design more and more expendable launchers, and you can see that the Americans have just backtracked even from some of that. The actual aircraft industries, the Boeings, the Lockheeds of this world, are obsessed with scramjets, despite the immense technical problems. But of course, they have a vested interest in building more of these expendable vehicles, and they're not going to be short of research funds for a long time to come. The pre-cooled engine is here. It's not something in the distant future. It will get us to Mach 5, And I've already shown you that on the rocket equation basis, Mach 5 gives us a very, very good leg up into orbit. We in the UK, and this is going to be my only political statement tonight. Oh, sorry, I mentioned Kenneth Clark, but that's not a political statement, it's a personal one. We alone in the UK have got the technology to do this. And I'm very pleased to say that in recent times, we have had a very, very positive attitude from not only the British National Space Agency, but from the European Space Agency. Reaction Engines has just done a trade mission to the States, and we've had very, very positive reactions from the United States as well. But there are problems with dealing with the United States because of the international trade and arms regulations, and it doesn't look as though we will be able to involve the United States in the development of this vehicle. So on that point then, I just want to sort of say I'm very indebted to everyone at Reaction Engines. We've now grown to about 35 people. They are so devoted to all of this that words fail me to express that. We couldn't have done this without private investment. Anthony Evans, Paul Portelli, who sadly is no longer with us, and Nigel McNair Scott, who was also inspired by Project Daedalus. And the reason that he has been prepared to support this is from a study that was done a long, long time ago, 40 years ago, and he's quite happy to support what we're doing. And of late, I need to say that the BNSC have been outstanding, and especially Ian Gibson, who retires at the end of this month, but I'm pleased to say he's leaving quite a number of disciples behind him, and so I think that the support that we get there will continue. And that's it.